system.
Okay. I think we can have the recording now. Yeah.
Okay.
Okay,
Yeah,
sure.
we should probably start. Do we start now?
Yeah, I can. Let me change the
So
cursor.
we're very glad to have Da-Chuan Lu talking about their new work about Fermi surface anomaly and symmetric mass generation.
Yeah, thank you. Thank you for the great opportunity to for me to present our recent work on this Fermi surface anomaly and symmetric mass generation. I'm Da-Chuan Lu from UC San Diego. And first, let me thank my collaborators, Mengzeng and Yizhuang Yu from UC San Diego, and Zhu Wang from Harvard. And in this talk, I will mainly focus on this second reference. It's about the definition and classification of the Fermi surface anomaly. If I have time, we will discuss the first. Oh, sorry, what's the duration for this talk? It's
it's usually like as long as like 1.5 hours. So you should take time. It's you can go 1 hour or 1.5 anytime between.
Okay. Yeah, thank you. Yeah, I have many things to say, so that's great. And feel free to interrupt me if you have any questions. And make this presentation more clear. Okay, so so I would like to motivate this talk by first reviewing something about the Fermi liquid. So let's first take a look at the Fermi liquid effective action. So the Fermi liquid contains many. So if we are looking at the low energy physics of the Fermi liquid, there are many gapless particle pairs around the Fermi surface. So in the left figure, we are showing that the electron at the P1 and the hole at P2. So both of these excitations are really close to the Fermi surface, and they are the low energy excitations. The action for this free fermion system is in this form. And here are some very good review about the effective action of the Fermi liquid theory by Polchinski and Shenka. And from the maybe undergrad solid state physics, we know that Fermi liquid is very stable. It describes the most electrons in the normal state of most metals in the low temperature. It's a very good description, and moreover, from the effective field theory point of view, we can really understand why this Fermi liquid is against interaction. Here we show two different types of momentum transfer. If we take two momentum points at some arbitrary position, then this four fermion interaction will be irrelevant. But if they are at the antipodal of this Fermi surface, then this four fermion will be marginal. And for the forward scattering, the four fermion interaction will be marginally irrelevant. So that's why the Fermi liquid is stable against the interaction. The interaction will just renormalize the free fermion theory. And if we linearize the free action, we can actually get a circle of gapless fermions. They are like the circle of a chiral fermion moving along the normal direction of the Fermi surface. It's a well-known theory, but we would like to ask the question that what protects the gaplessness of this Fermi liquid? Since recent analysis of recent works on the anomaly and generalized global symmetry make us understand more about the gapless quantum physics of matter. They are mainly arise from the anomaly and emergent symmetry. So at this point, I would like to give you maybe two examples and then come to the Fermi liquid. The first is the deconfined quantum critical point, and the second is the superfluid insulator transition. So they are both gapless quantum phases and with anomaly as well as emergent symmetry. So for the deconfined quantum critical point, it describes a second order phase transition between two spontaneous symmetry breaking phases. On the left hand side is the new phase. So you can see my cursor, right?
Yeah.
Okay, cool. Yeah, left hand side is the new phase. It describes the spin, the spontaneous symmetry breaking of the spin rotation symmetry, and it looks like this. It's an antiferromagnetic order. And the right hand side is the valence bond solid phase. The two sides are combined to form a spin singlet, and it breaks the rotation symmetry of the system. So if we proliferate the defects in the VBS phase, very interestingly, the core of the defect will carry the spin 1/2 degree of freedom. So if we proliferate the defect, it will melt this VBS order. But due to the additional spin 1/2 degree of freedom, it will break the spin rotation symmetry and get to this new phase. The low energy field theory description of this DQCP has the mixed Hopf anomaly between the spin rotation symmetry and lattice rotation symmetry. So the consequence of this mixed Hopf anomaly suggests that the low energy phases should be either gapless, which is the DQCP point, or spontaneous symmetry breaking of either symmetry, such as the spin symmetry, then this is new phase. Spontaneous of lattice symmetry is the VBS phase. And it also suggests that there could be a topological order, but we are not sure what's the topological order saturates this anomaly. These are many various interesting IR phases, but the Hopf anomaly forbids the symmetric gap phase. So there is no way to get a symmetric gap phase with unique ground state. They should be either gapless or spontaneous breaking or topological order. And furthermore, there is many signature that this DQCP has emergent larger symmetry, such as SO5 symmetry. In the maybe lattice model, in the 1+1D in the 1+1D DQCP, the U1 cross U1 symmetry had enlarged to SO4, something like this. So it really contains this emergent symmetry. Are there any questions so far?
Where does this emergent symmetry appear? Like, where in the phase diagram are you starting off at when you're describing the low energy field theory?
Oh yes. So if we consider the order parameters, the VBS the order parameters for the VBS phase has two order parameters correspond to like this valence bond in the X direction or in the Y direction. Mm-hmm. And for the new phase, the order parameter can be like S, X, S, Y, and S, Z, the three components of the spin operator. And at the critical point, there are some arguments that this three component order parameters and the two component order parameter combine together to get a 5 component operator. And this operator is symmetric under the SO5 rotation symmetry.
I see.
But yeah. that symmetry doesn't tell you that the defect of one is carrying quantum number of the other, right?
Yeah, that's right. The emergent symmetry doesn't tell about the defect of one symmetry breaking phase contains the quantum number of the other. But this really comes from the mixed anomaly between these two symmetries. Is that correct? Mm-hmm. Yeah. Yeah, maybe, yeah, actually I'm thinking about more general more general description of this DQCP. So if we have some term like that describes the disorder operator in this symmetry breaking phase, and another disorder operator in the other symmetry breaking phase, we can construct the west to middle Witten term to describe the mixed anomaly by linking like by linking these two different disorder operators. Yeah, I think that's beyond this talk, and we could discuss this afterwards. Okay, but yeah, really, this DQCP, the gapless is ensured by this mixed anomaly, and the emergent symmetry could be a consequence of this gapless state. And another example is the superfluid insulator transition. This is quite well-known that and and has a long history. For example, we take this complex scalar field in 2+1D. And on the left-hand side, we have the boson condense. It gives this U1 zero form spontaneous symmetry breaking. And so we have this superfluid phase. But if we we drive this boson to gap phase, then the U1 is symmetric. And based on recent works on the generalized global symmetry, according to this works, there is actually an emergent U1 one-form symmetry correspond to the vortex conservation in the superfluid phase. And it's been argued that this U1 one-form symmetry still exists at the critical point. So at the critical point, there is a mixed anomaly between the U1 zero form symmetry and the U1 one form symmetry. So this is argument for this this well-known superfluid insulator transition is also protected by the mixed anomaly. And the emergent symmetry is this U1 one form symmetry. If we have a d spatial dimension, then this emergent half form symmetry will become like the U1 d minus one form symmetry. Yeah.
So the mixed anomaly also exists on the condensed phase, right?
Also, yeah, it's also exists in this superfluid phase, but the U1 one form symmetry explicitly broken in this insulating phase.
Yeah.
So we will not get this mixed anomaly.
Right.
That's right. Okay. And next is our talk about the Fermi liquid. So the Fermi liquids, we can take the Hamiltonian for this Fermi liquid, and this theta. Can you see this figure? So this figure, we are just take a Fermi surface and parameterize by this theta angle. And this n theta is the number operator counts the fermion numbers at different points of at this Fermi surface. So this theory has an emergent loop U1 symmetry. This loop U1 symmetry has this transformation. That is, it takes the fermion operator, rotates the fermion operator at different position with different phase angle. This phi theta could be thought of as a continuous function. And it has the equivalent relation, phi theta is equivalent to phi theta plus 2 pi. This equivalent relation basically means that this is a compact U1 group. And to give some more intuition about this loop U1 symmetry, we can consider there are subgroups. For example, here I list some lowest order subgroups for this transformation. if we have the total total charge conservation symmetry, like the total U1 symmetry, it means that the this phase rotation is actually a constant number. Then we can imagine that rotates the fermion on this Fermi surface by, like, let's say a positive phase and denotes by this red color. And there are another very interesting subgroup correspond to this translation symmetry. If we translate in the x direction, then it will like makes this red part of the Fermi surface rotate with positive phase, and the left part of the Fermi surface rotate with negative phase. And correspondingly, this describes the translation in the y direction. You could imagine there are higher order subgroups like this D-wave black subgroup, and maybe we can think about it like the squeezing in the vertical direction and stretching in the horizontal direction. So there are higher order subgroups of this loop U1 symmetry.
So is it can we true that we can also think of those as generators of diffeomorphism of a circle?
Diffeomorphism of the circle. I think if you are allowing the circle to be deformed, then that will cost energy. But if you are mapping, yeah, how to say? I think there are some relation, but there needs some more work to show how they map to each other.
It doesn't look like a diffeomorphism. It looks like a gauge transformation on the circle. Right?
Yeah.
You have a circle, and at every point you can do this U1 transformation, but it's not moving the momentum. Right? Not one momentum.
That's right.
I see.
Yeah.
Thanks.
Yeah. So for the diffeomorphism, I think there is a paper by in Danson's group that canonic transformation actually has some energy cost. So it really moves your Fermi surface and really like change your shape of your Fermi surface. Then that will cost energy.
I guess there's two ways to change the Fermi surface. One is to change the shape. Is it true that there's another ways to go tangent to the surface, like move the point from one point to another near the surface?
I see, but that will create like the density modulation along your Fermi surface, right?
Right.
And maybe that will also cost energy.
I see.
Okay. Yeah. Are there other questions?
Yeah, just to clarify, so you have this model that has this LU symmetry, and you're just breaking up these LU1 symmetry into these subgroups that correspond roughly to these pictures of, like, you know, D wave and higher order, like finite rotation.
Okay. Yeah. So actually, still have this loop U1 symmetry, and here just showing some very interesting subgroup of this loop U1 symmetry. So in the low energy, we still have the very large emergence symmetry, this LU1 symmetry, and this very large symmetry contains this several interesting pieces.
Right, and so those are going to be the things that you use to characterize the excitations. These subgroups are like you're interpreting them.
Oh yeah, that's correct. I'm going to show that this total U1 translation symmetry actually come from the UV lattice model. Does this make sense?
Excuse me, one clarification. It seems that these different subgroups are like spherical harmonics on circle. So is it that you have just accepted that local function pi of theta and spherical harmonics?
Yeah, I think that's a good way to think about this transformation. But actually, how to say? If you want really write down a symmetry transformation operator, then that corresponds to a multiple fermion product together. then that's a very complicated Fermi symmetry symmetry charge operator.
How come translation is maybe this is really how come in the subgroup if I multiply it twice, shouldn't they get a winding number of 2?
Sorry, I can't hear very clearly. Let me increase my volume.
If you multiply this translation twice, don't you get a winding number than just the?
Yeah, then this phase will be like 2A dots kf. If we take this A is a translation vector. For example, it's if you take the translation in the x direction, then it's basically ax times kfx.
Okay.
Then if you translation do the twice, then this A vector basically times 2.
So how come it's not D-wave like? The D-wave like one, I assume, winds twice around the circle. So then how come multiplying 2 single windings doesn't generate a double winding?
KF is periodic in theta.
The phase rotation is at each point of this Fermi surface. So if we take a look at some point at here, then you do like 1 unit of D wave like transformation, then it rotates like minus pi/3. If you do it twice, then it rotates the phase by like minus 2 pi/3. But if we look at this point, then it rotates by pi/3 and 2 pi/3. Does this make sense?
The question was about, I guess, about a different set of functions, phi of theta, which wind around the Fermi surface, which I guess you're not showing, right? These things all have 0 winding.
Yeah, this one doesn't.
Oh.
Really,
Yeah.
This is rotation of the Fermi surface.
So another set, you mean that's a theta, phi theta plus 2 pi?
You could consider phi of theta to be a function that is only periodic modulo adding multiples of 2 pi.
Okay.
Which I guess is also part of the group, right?
Yes, but that's under the equivalent relation. It's equivalent to phi theta.
Oh, I think the winding thing is like phi theta equals theta, and that kind of the winding. And what you have is like phi theta is like cosine theta. It's all these things with 0 windings.
Yeah. Here is all 0 winding, I guess.
Okay, thanks.
Yeah, sure. Okay. And this part I'm going to talk about the UV-IR matching. So the Tohoff anomaly is a renormalization group invariant, means that the Tohoff anomaly of this UV symmetry should match with the IR symmetry. And if we add some symmetric operator to trigger the RG flow from the UV theory to IR theory, the Tohoff anomaly should still match under the RG flow. And the UV symmetry, if we just thinking about the lattice model, we have the fermion hopping on the lattice, then it has the translation symmetry as well as the charge conservation U1 symmetry. And because this translation symmetry acts in a non-onset way, that means this transformation is not onset. So there is a mix. If we transform this into some symmetry groups that acts onset in the IR theory, then this symmetry, this onset symmetry will have the mixed Tohoff anomaly. And because of this mixed Tohoff anomaly, this anomalous theory should, like in this picture, should attach to a bulk SPT. Maybe one way to think about this example is like if you have a 1 plus 1D chiral fermion. Oh, sorry, 1 plus 1D fermion model, gapless fermion model. Then it has U1 vector symmetry and U1 axial symmetry. And these two symmetry has a mixed Topov anomaly. You can attach this gapless theory to a 2 plus 1D chain insulator. So that's a basically this picture means. And more detailed analysis about this lattice and field theory correspondence are in this 2017 paper. So for us, the question would be, what is the bulk of the Fermi surface? It means that
Sorry, can you say again your example? Is that 1 plus 1D chiral fermion or 1 plus 1D just 1 plus 1D massless fermion?
Just a 1 plus 1D massless fermion.
Why it has to couple to a bulk chain insulator? I thought chain insulator's boundary is chiral fermion.
Oh, you can have double chain insulator. Okay, maybe that's not a good example. Let's see.
I think the boundary is a chiral fermion, and then the bulk is a chain insulator, right? If the boundary is a helical fermion, then the bulk is more like a quantum spin Hall effect. It's like left.
Yeah.
So I'm not sure why you say it's SPT here, because that's suggesting the boundary is not chiral. But I thought the Fermi surface case is the chiral.
Yeah, I think it's using the SPT in a more broader sense. Let's say including chain insulator as a.
Yeah, you can include the invertible phases.
Symmetry protected usually means that it could be destroyed if you break the symmetry. But so the chiral phases are not like that. They are more intrinsic.
Okay, I see. But there are gravitational anomaly.
Yeah, so they are more intrinsic, more robust than SPT.
Yeah. I would say this okay, right. If we are only consider the mixed anomaly of the symmetries, then it should attach to a SPT. But if you are just anomalous theory because of the gravitational anomaly, then your bulk is some invertible topological order. Is that correct?
Okay. Yeah.
Also, just to make sure your claim, are you claiming symmetry and anomaly is a necessary condition for gapless phase, or a sufficient condition, or both, or neither? Just want to.
Yeah, from this point of view, okay, so we are I'll say the claim is that okay, so the thing is that we find many examples that if you have the anomaly, then you will get the gapless phase with emergent symmetry. Okay, and we want to ask if this Fermi surface there, Fermi liquid theory also fall in this category.
I see.
But we didn't make a very strong claim that every like gapless spaces are protected by anomaly.
Yes, good. Thanks.
But I think we have many examples. Certainly the gapless space are protected by various anomaly.
And just to be clear, when you say Topov anomaly, like, is the general definition here just kind of this mixed symmetry, or?
Yeah, so the mixed Topov anomaly means that for example, in the DQCP theory, if we just okay, let's go back to the DQCP theory. So here is some symmetry G1, and here some symmetry G2. The mixed anomaly basically means that the disorder operator of this G2 symmetry breaking phase carries the quantum number of the quantum number of this G1 symmetry.
I see. So that is the definition.
Yeah, in general, if you have two symmetry groups, your tensor product together, you won't have. If you don't have the anomaly, then you won't have this feature.
Yeah.
Do something for the one symmetry that will have some consequence on the other symmetry. That's not the case. But if you have this mixed Topov anomaly, then do something in the in one symmetry will have some consequence in the another symmetry.
Okay.
Yeah. Also, yeah, maybe you have some domain wall, and the domain wall carries the quantum number of the other symmetry. That's another way to say this. Okay. So then here it comes to my outline. I think, I'm spending a lot of time to motivate the problem, but I think it's good. So the outline will be that we can think of this Fermi surface as the boundary of the Fermi C, and this Fermi C is actually equivalent to the phase-space chain insulator, showing in this 2015 paper. And if we do the dimension reduction, we can get back to the Fermi surface. If we couple this space chain insulator to background gauge field, we can integrate out the fermion and get this response theory. The response theory really captures the loop U1 anomaly inflow of this Fermi surface of the Fermi liquid theory. And there's another part is about the classification of the phase space chain insulator. So, are there questions?
No.
Okay. So for the classification problem, we can do the synthetic dimension reduction to get this phase space chain insulator to a 0 + 1 DSPT. Here we should see that the Fermi surface in this diagram is only codimension 1 Fermi surface. Okay, so let's first talk about this first part. How do we think about the phase space chain insulator as a Fermi C?
Are you going to explain what is that dimension counting? D plus D minus 1 plus 1?
Oh, okay. Yeah. The D dimension. Okay, the first dimension is a real space dimension.
Okay.
And D minus 1 is it's a Fermi. Okay, it's a for example, if we have a codimension 1 Fermi surface, then it's a D minus 1, like in momentum space.
Good.
And the next one is the time.
So that dimension is not the dimension of Fermi surface.
Why do we need to add the Fermi surface dimension to the spatial dimension?
Like for example, if I just have a 2D free fermion, that Fermi surface is 1 dimension.
Yeah. Right. This okay. So if we think about this Fermi surface in a phase space, then it's this counting. But
which means there's D position and D momentum. And
yeah.
There's D minus 1 dimensional Fermi surface. So D
Right.
and D and then time.
I see. Thanks.
Okay. Yeah, I will present more pictures about
Omega. It's like there's time, no frequency, but there's position and momentum.
All right. Okay. Okay. So yeah, the first part. Let's just be very simple. Think about 1 + 1D massless fermion. So we have two chiral mode at minus KF and KF. So there is a left moving mode and a right moving mode. So we can think about this 1 + 1D system. They contain 0D Fermi surface, and the Fermi C is 1D. So we can think about this two mode as the boundary of this chain insulator. But this chain insulator have a position in x direction and momentum in y in the vertical direction. Okay, so yeah. So let me maybe first remind you the chain insulator in real space. So if we have this Hamiltonian, this sigma x, sigma y, sigma z are the polymatrices. They are anti-commuting with each other, and we have a mass profile. So inside the chain insulator, we have negative mass, and outside we have the positive mass. So at the edge, there is a chiral mode travel along in one direction along the boundary. And now we are substitute this y direction by the momentum k. But is this a correct way to think about the like is this equivalent to this by just replace y to k? We should still think about the non-commutative nature of the position and the momentum. So there are actually two ways to implement ensure this commutator. One is by threading the phase space barrel curvature through the xk plane. So if we have this flux through the xk plane, it's like you put some lowest Landau put the fermion in the lowest Landau level, and these two coordinates doesn't commute. Another way is just quite simple. In the quantum mechanics, we can do the canonical quantization, and the operators are related by this by this relation. So we can next we want to show that the phase space chain insulator can reduce to the Fermi C by the dimension reduction. So let's take this Hamiltonian of the phase space chain insulator, and with this mass profile. The mass profile we are taking is that it's negative inside the minus kf to kf, and the positive otherwise. And it actually does not have any dependence on the position. So we can.
Sorry, I have a question.
Yeah.
A simple question. So usually, if I consider the 1D fermion, then the psi only depends on x position, and its momentum position dependence is because of the Fourier transformation, right? The psi, we write it psi e to the ikx. Here,
sorry, yeah, the set dagger, we are putting this fermion in the phase space, so the coordinate actually contain both the x and k, and therefore this psi operator is a function of both x and k.
Okay, then does it? But now you have this partial x. Is that partial x equal to k or partial x?
Partial x equals to k, and there's actually a subtle question that how do we interpret this k? And maybe we will come back to this later. But in short, the partial x is substitute to k if you want.
But I don't know. But you are writing psi. I thought that this Hamiltonian means that every x and k you define independent psi. Is that right?
Yes.
So then partial is not k because there's two independent coordinates.
Right. It's actually k tilde. It's something like a momentum. If you do the Fourier transformation, then it's like that another like k tilde is another coordinate.
Okay, so I can just think about k was the canonical conjugate of the y, but then in addition you impose x k non-commutative. So it's really it's a 2 + 1D fermionic system, but on non-commutative geometry.
Let me rethink about your construction. So k is a conjugate to y, and
but then in addition you require x and k to be.
No, but so we will still impose the x and k has this non-commutative relation. We still impose this condition, but instead of
but
x
then there's
y.
like x on like x commute with k equal to I, and also x commute with this k tilde. This partial x is also equal to I. So there's two operators that the Poisson bracket with x is equal to I, right?
I think the best way is to think that these fermions modes are written in the wavelet basis. In the wavelet transformation, you are not labeling your basis only by momentum or only by position. The position is like the center of the wavelet. Momentum is more like the internal structure of the wavelet. And so such that you are able to label your modes by both of them. And there's a, that's the common. And it is still a 1 + 1D system.
So still a 1+1D system.
Yeah.
Okay.
Yeah. Maybe I can jump to the. Yeah. Maybe let me jump to the. There's a picture. So we can think about this xk. So in the phase space as some lattice, and it has a lattice constant like ax with some large spacing. And under the Fourier transformation, we get another k tilde x tilde, but with very small spacing. So this k tilde actually so originally this k we just look at this k. Then this k really means that it corresponds to some large momentum transfer mode. But under the Fourier transformation, the k tilde is something that's very short. So then they are capture the very finer structure inside the momentum spacing. That is make sense.
Excuse me. Why k tilde is not k? Like x and k were like Fourier, like they were conjugate of each other, Fourier conjugate.
You mean why do we use this phase space?
I was hoping when we take Fourier transform of this x comma k phase space, k and x would interchange.
Yeah, x and k are not Fourier transformation to each other in this case because they are both label of the wavelet, and then they are independently.
I think maybe the general setup wasn't clear because I mean, please realize that this is mainly a group of high energy. So sorry, but so the setup is that you want this theory which is defined like when you call it phase space, you treat it as if it's just an ordinary like real space, and then you want this two-dimensional from this two-dimensional real space. When you have this magnetic field, then it becomes like a phase space of the d-dimensional theory. So you want this relation between S and K to not be given, but emerge from when you have a magnetic field and then occupy the lowest London level.
Sorry, I mean, I just
How
start
does the
with.
magnetic field like introduce essentially the canonical commutation between x and k? Or is that like what we're gonna talk about?
Do you have someone? Do you have? Yeah, this is.
Okay, I see.
Yeah, there's two ways to implement this commutator.
But physically, it means that you write down that theory in xk space where the like x and k were originally they were commuting, but now you add this magnetic field. If you look at the lowest London level, then they are not commuting anymore. So that's
Yeah.
But I thought for this Fermi surface effective theories, you have all the spatial dimensions and then d-1, like the slide before this one, maybe like d plus d-1, yeah, this thing.
Yeah.
But that's different counting from what you're doing right now. Like right now you have 1 plus 1. You don't have 2 plus 1 plus 1.
Yeah, the bulk phase space chain insulator is 1 plus 1.
Yeah. Okay.
Yeah.
I see. So you're having this high dimensional system where you're treating all the momentum variables as like independent variables evolving in time, and you're going to use the magnetic field to in the correct phase space of this lower dimensional thing that you're trying to capture.
Yes, that's correct. Yeah, right. So if we write in the phase space, we are thinking the x and k actually just some classical coordinate, and by imposing this either this phase space spiral curvature or canonical quantization, we can get back to the correct commutator between the x and k.
So
and we are yeah.
Multiple such x's, k's that should anti-commute. Can you always find a magnetic field profile that will do this?
We only need to thread the flux through this xi-ki plane. So if you are in a higher dimension.
So you can do it for each of them.
Yeah.
Yeah. Right. So this is really the this space chain insulator is really the bulk description of the Fermi C. Sorry, Fermi surface. Because if we because this mass term changing sign when go across the KF, then they are correspond to some localized mode at this minus KF and KF. If we do the domain wall construction, we can reduce this Hamiltonian to the left mover and the right mover. So this really shows that if we project this phase space chain insulator to its to the boundary in the momentum space, then they are correspond to this chiral modes. Okay. Yeah, and this construction can be generalized to higher dimension. So if we have the deep space time, D spatial dimension, then this the Hamiltonian looks like this. This gamma x, gamma k, and gamma 0 comes from the complex Clifford algebra. So they are anti-commuting with each other. The mass profile is it's a negative inside the Fermi C and positive outside the Fermi C as usual, and it does not have any dependence on x. We can similarly do this dimension reduction by maybe let's say we can choose to project the chain insulator to this in this direction, in this K1 direction. Okay, so this mass profile will change sign along the K1, and it's negative. It's negative inside the. It's negative on the left part of the Fermi surface and positive on the right hand side. So next, we just project this out. We get a localized mode, and next we can use our canonical quantization to change this IK to X. That imposes a commutator between X and K. So note that this part, where's my cursor? This part becomes the X in from X2 to XD, and this are really give you additional domain walls, additional sign changing. If we think about this as sorry, there's no I here, sorry, but it's really like the mass term in your chain insulator, and we can further project these pairs. They are pair up and can be project out. So we are leaving with this chiral fermion along the X1 direction. Just as
when you say project out, it just means they have a gapless spectrum, so you focus on the 0 mode.
Yes, that's right.
Not the low-lying mode. Okay.
Yes. So finally, if we do this projection, like in the different parts at this Fermi surface, we will get this the bunch of chiral fermion flow like moving along the normal direction of the Fermi surface. There are.
So to be clear, since you can always do this, does that mean like the churned insulator low lying excitations like above the full Fermi surface are like fully characterized by all these projections?
Yes, I think so.
Okay, and there's always if you know like the different projection modes, can you uniquely pick out that churned insulator there?
Oh, sorry, different mode. I think here we have the bulk chain insulator, and you push to the boundary, you get a circle of this chiral fermion.
Yeah, but if you were to try to do the reverse, to try to reconstruct the Fermi surface, can you pick it out? Or
But-
maybe not just the Fermi surface, but just the bulk.
Oh, oh, you want to like, yeah, that's I don't know, but we can certainly find a bulk and that has this boundary.
Yeah.
Yeah, the reverse problem is not I think this procedure is not invertible somehow, because the projection of matrix has 0 eigenvalues and okay. Okay.
Sorry, actually, I'm still a little bit lost. So, sorry, can I clarify what's the procedure? I choose a specific direction in a d-dimensional Fermi liquid, and map that direction as a boundary of a 2D bulk, or
Yeah, just to go back this 1 + 1D example.
this one is clear. But I mean, for higher dimension, what's the procedure? You first choose a specific direction for your Kepler
Yeah,
system?
yeah, because the mass term is actually a vector here, right? But let's do simple calculation just to choose the one direction, like a k, the one specific direction of this this vector.
Okay.
And in principle, you should carry this calculation over the whole vector that parameterize this Fermi surface.
Okay, maybe let me try to formulate my question in a different way. So I'm worried about if you have a d-dimensional Kepler system, the bulk is not a d+1 dimensional chain insulator, right? Because chain insulators only exist in even dimension.
Chain insulator, sorry, you are talking about the space dimension of
Space.
Okay, yes, right, that's correct.
So, for example, if I do this procedure for a 4D gapless system, the bulk would be a 5D chain insulator, definitely.
Okay, so here we are focusing on this codimension 1 Fermi surface. So if you have a 4D space, okay, so 4D is spatial, right? Spatial dimension.
Yes.
Okay, 4D spatial dimension, then your Fermi surface is 3D, right? Right?
I think here the chain insulator is always defined in the even dimension because it's a phase space chain insulator, not the real space. Phase space always contains real space plus momentum space, where the space always.
I think sounds good. Thanks.
Yeah. Okay. Right. So yeah. Right. So like in this D dimension, then it's a 2D + 1 phase 2D + 1 chain insulator, phase space chain insulator. Okay, and so from this part we are seeing that this boundary model contains independent fermions propagating along the normal direction at every kf on the Fermi surface, and these are the directional fermions and match the low energy degree of freedom of the Fermi liquid. So we can also see the emergent loop group symmetry, which comes from the bulk U1 symmetry. The bulk U1 symmetry is a U1 symmetry for the phase space chain insulator, and the boundary theory has this emergent loop group symmetry. Okay. Okay. Next, let me talk about the response theory. It's correspond to the 2D + 1 Chen-Simons theory. So like in the ordinary chain insulator, we can couple this theory, a minimal couple this theory to a background gauge field. This dx and dk are the covariant derivative in different direction. And by after integrating out the fermion, we can get this Chen-Simons term. This is a 1 + 1D system, so we get 3D Chen-Simons theory. 3D Chern-Simons theory. And there is it's the Chern-Simons term only exists inside the chain insulator because this sign changing of the mass term. Okay. And as we said before, that we need to insert the flux to ensure the commutator relation. So by inserting this flux, we can reproduce the Latinger theorem by doing the variation about this action with respect to the A0 component, and this gives you the filling of this Fermi liquid in 1+1D theory. So here is the table for general dimension, and maybe some at least just to 3 dimension, then you get the 7 form. If your Fermi state is 2 dimension, you have this 5 form. But one very important thing is that you need to thread the background flux through every xi ki plane, and this is quite different from the ordinary Chern-Simons theory. Are there questions so far? And actually here we have a natural question, is that so since we maybe let's take a look at the Fermi surface dimension 1 and the phase space dimension 5. The bulk Chern-Simons term is this 5 form. So ordinarily this 5 form Chern-Simons term can be thought of the bulk of a well fermion in 3+1D. But does this mean that the Fermi surface in 2+1D is equivalent to the well fermion in 3+1D? Certainly they are quite different, and the difference actually comes from our 5D Chern-Simons theory needs this flux constraint. Another argument, another way to say they are different is that if we break the U1 symmetry to Z4, then the Z4 symmetric well fermion have a non-perturbative anomaly, which is Z16 classified. So if you have the 16 copies of the Z4 symmetric well fermion, we can trivialize by having by interaction and have a unique ground state. However, this is not true for the Fermi surface with Z4 symmetry in 2+1D, because in 2+1D we can add this charge 4e interaction, so which is totally symmetric under Z4 symmetry, and if you tune this interaction to large enough, we can get you can get a unique ground state with this product state. So this means that 2+1D Fermi surface with Z4 symmetry is Z4 classified instead of Z16. And this interaction drives the system to gap phase is called the symmetric mass generation, because it does not break any symmetry, and it gives you gives the Fermi liquid some mass. So yeah, here comes to the final part of this the anomaly of Fermi liquid. It's the classification problem. So we can do the synthetic dimension reduction to get the 0+1D SPT from the phase space chain insulator. So start with this box phase space chain insulator, and we substitute the I partial k to x, and this x as previous, it's like creating many domain walls along different directions, and we project to the 0 modes, then we get only this mass term. This is just a 0+1D system. So here are some comments. So the M tunes the topological transition of this box theory, and the box state is trivial if the gapless fermion mode at m = 0 can be symmetrically gapped by interaction. So therefore we could get interaction like the classification of interacting SPT by just classify this 0 plus 1D dimension system.
Sorry, so why physically, like, why is this reduced to 0 plus 1 rather than like 1 plus 1 chiral fermion?
Wait, 1 plus 1D chiral fermion. Oh yeah, because if we want to classify the SPT, we kind of how say, we kind of don't have the open boundary, right? Then there's if we move slowly in the Fermi surface, inside the Fermi surface, inside the Fermi C, then this M can be taken as a constant.
Okay.
And this is really the classification of the bulk SPT instead of the classification of some gapless chiral fermion.
And so the Z4, but so like, let's say, for example, in this Z4 you mentioned, does that mean the gapless excitation near the Fermi surface is also classified by Z4?
Gapless excitation. I don't sorry, I don't think so, because the gapless degree of freedom is correspond to some free theory. But the Z4 is interaction effect.
So what happened? Maybe I'm lost. So when you turn on this interaction,
yeah, let's go back to this part.
You have Fermi surface?
Yeah, in general, you have Fermi surface. For example, we can take the Fermi surface. We can take a square lattice, and the Fermi surface is, if we take half filling, then it corresponds to a square Fermi surface in this problem.
And what do you mean? It's a fourfold?
Oh, fourfold means that we just take a full copy of this half filling Fermi C.
But you are saying, like, when the symmetrical gapped phase is when Fermi surface is also gapped?
Right. So the Fermi surface is gapped out by this interaction, and we can get a unique ground state with this product state.
Okay.
Right. This classification only gives you part of the anomaly in the Fermi to characterize the Fermi liquid. Let's maybe get to this table. So this 0 plus 1D, if you classify this 0 plus 1D system, this gives you this integer index. And there's another part in the anomaly. It's the filling fraction of your Fermi liquid. So and for example, we take this Z4 symmetry, Z4 and maybe a full copy, we can get a unique ground state. Sorry, a 1/2 and 2, 2, 4.
I'm confused about I thought the classification you listed here responds to some anomaly at the Fermi surface. But you were saying when you have a symmetric gap, then you gap the Fermi surface.
Right. That's a class. Okay.
The bulk is trivial. Okay.
Yeah. That's because it's the interaction will reduce the classification. Like if we have full copy of this psi I dagger psi G, so if we just ignore this A label, the A labels the fermion flavor.
So in the case in the non-trivial case, when you have non-trivial, like when you have the 3 non-trivial classes of the Z4, then they correspond to non-trivial like space at the Fermi surface.
Sorry. What's a 3? What's a 3?
Well, Z4, there's 4 classes. There's 3 of them which are non-trivial.
Yes, 3 of them are non-trivial, because if you have 3 copies, then you cannot add this full fermion interaction.
So when they are non-trivial, what happened to the Fermi surface excitations? Like, do they like say it's does that mean they carry some anomalous? What kind of anomaly do they carry?
They are still Fermi surface and they are still gapless. And this gapless we are interpret as it has a Fermi surface anomaly.
So they are actually adiabatically connected to the free case.
Yes.
Okay.
Yeah, because you cannot add the interaction. I think it's free. Right. Only if you have the 4 copies of this system, you can add this charge 4e interaction. Right. If you preserve the Z4 symmetry.
Okay.
Right. That's correspond to like so yeah, maybe another well, another example is Fitigowsky-Kitaev interaction. If you have the like 1 copy of Majorana chain, then you have a dangling Majorana zero mode as a boundary. And if you have 8 copies of them, so if you just look at the boundary, then you get 8 Majorana zero modes. They are gapless. But you can add the Kitaev-Fitigowsky interaction corresponding to the 4 Fermi interaction to gap out the 8 Majorana zero modes. And also respects the symmetry.
Okay.
Yeah. So right. So here the non-predictive anomaly classification is obtained by like saying how many copies we can have and what's the interaction we can drive these copies of Fermi liquid of gapless Fermi surface to gap phase. Okay. Should we move on?
Yeah.
Okay. Yeah, and maybe another generalization to this problem is that if we have the codimension not 1 but 2 or 3 Fermi surface, then the argument then the classification problem is corresponding to the classification of this D effective SPT. So for example, in 3+1D space time, if we have the codimensions 2 Fermi ring, then it's a classification of 1+1D system with U1 symmetry, and the classification is 0. This because the Fermi rings are not stable in this 3+1D. And if we are having the codimension 3 well points, the classification is Z cross Z. This because that there's some 2+1D interface between the 2 well points. We can attach different quantum Hall number or the thermal Hall number to the 2+1D interface, and this gives you the Z cross Z classification. Yeah. So should we do we have more time? I can describe the Fermi surface symmetric mass generation.
Yeah, we can continue for another 15 minutes or so.
Okay, that's enough. Okay, so the symmetric mass generation means that so symmetric means that we need to preserve certain symmetry, like the of interest such as the time reversal, charge conservation, or chiral symmetry. And mass means that we want to the gapless fermion become massive, and this can be seen by 2 ways. One is there is an energy gap in the dispersion. This is a free fermion description. Another is we can have the many-body excitation gap characterized by the exponential decay of the correlation function. And the generation means that this is a dynamical process. And by adding the symmetric interaction, we can develop the multi-fermion condensation that preserves the symmetry and open the gap. So the necessary condition for SMG is anomaly free. And why do we care about the symmetric mass generation? The ordinary mechanism to give the fermion mass is through this Anderson-Higgs mechanism. So it basically corresponds to condense the fermion bilinear mass. But this will necessarily break the symmetry. So it's not symmetric. This SMG was also was proposed in Aitken and Presque in 1986 to realize the chiral fermion theory in the lattice model by symmetrically gap out the mirror sector. And this was recently numerically confirmed in this paper of a 1+1D chiral fermion model. So in this talk, I'm going to talk about the Fermi surface symmetric mass generation. This can help us to understand more about the strongly interacting system with finite density, such as the pseudo gap in cuprate superconductors and large Fermi surface to small Fermi surface transition, something like these problems. And let me spell out the Fermi surface anomaly vanish condition. Is that this anomaly equals 0 mod 1. And this anomaly index contains like two parts. One part is integer anomaly, and it's a charge times some multiplicity. For example, if it's a Z4 classified, then it's some number in Z4. And the second part is this Fermi volume. It's in general a rational number. It can be rational or irrational. And the vanish condition is that sum over all the Fermi surface is 0 mod 1. And here it's a very interesting toy model. We just consider two types of fermion. One type, the A fermion labeled by blue, is hopping on the Kagami lattice with U1 charge 1. And the B fermion hops on the triangular lattice with U1 charge 3. So if they are failing satisfy this condition, then the anomaly vanishes. The integer part is just the charge, and the failing part satisfy this condition such that the anomaly vanishes. So note that the U1 symmetry and translation symmetry are restrictive enough to forbid any fermion bilinear condensations, because the charge density wave will break the translation symmetry and the superconductivity will break the U1 symmetry. So there are some generic, there are some failing that satisfy this anomaly vanish constraint. However, we could add a symmetric charge fusion interaction, which is annihilate 3 fermion of this triangle and create a fermion in the middle, a B-type fermion in the middle. This form of interaction also appears in the recent quantum breakdown model by Biao-Lian recently. And in the strong coupling limit, the ground state is this product state, and it has a gap from all the excitations by order of G. So if we add this interaction and drive this to strong coupling limit, we can get the symmetric mass generation phase. We could further do the RG analysis of whether this SMG transition exists or not. So the symmetry allowed interactions in the figure A, it's dense-density interaction, two types of dense-density interaction. and the figure B is the charge fusion interaction. Yes, here we choose a very specific feeling such as the Fermi surface has Van Hove singularities. And this Van Hove and most of the density of state localized at this Van Hove singularities. So we can approximate this problem by just three hotspots. So by doing the RG, the phase diagram is like there's a Fermi liquid phase, all the interaction goes to 0, and there's a SMG phase, the interaction goes to infinity. So there should be a transition between this. There will be a transition between the Fermi liquid to SMG, but we don't know precisely what's the theory to describe this transition, or whether it's continuous or not.
So these interactions are not marginal in the Fermi liquid case.
Because of the Van Hove singularities, I guess. And also in the Fermi liquid, we calculate this RG equation is not marginal.
Okay.
Yeah, and let's come to the conclusion. So the classification of the Fermi surface anomaly is that the codimension P Fermi surface anomaly of symmetry group G is classified by this P symmetric interacting fermionic SPT in P space-time. And for the Fermi surface symmetric mass generation, it can happen when this Fermi surface anomaly vanishes. So there are many further applications and directions. That's all. Thank you for coming and many interesting questions.
Okay, thanks very much.
Yeah.
So I just coming back to the simplest case where you only have the U1 symmetry and translation symmetry, then I have a Fermi surface. In your classification, is that a case where it's non-trivial, like you couldn't have any symmetric mass generation?
Loop U1, so it's Z, but if you have some failing, like the fractional failing, then you could trivialize by if you have 1/3 failing, you can have 3 copies to trivialize this Fermi surface.
Okay.
So also, sorry, the charge should be like, for example, one layer with a positive charge, another layer with negative charge.
It's basically like superconductivity, like you have, so superconductivity parent.
But superconductivity will break the U1 symmetry.
Yeah, so it's like if I have a superconductor with a spin as Z conservation, then pairing between spin up and spin down would be
okay. Yeah, that makes sense. Yeah, that could be an example.
But these non-trivial cases like the one you're showing here, are they these non-trivial cases? They're not mean field. Like you can't do a mean field to get the gap space.
For the SMG phase, this product state you can just diagonalize this interaction to get the.
So this space doesn't have a bilinear order parameter, right?
You don't have a bilinear order parameter. You need to condense multi-fermion like this 4-fermion interaction. 4-fermion term. There's if you condense the bilinear, it will either break the translation symmetry or the superconductivity, I think.
Any other question? Okay, if not, let's thanks Da-Chuan again.
Oh, thank you.
Okay.
Okay.
That's that's interesting.
Yeah,
So
thank you. Yeah, thanks for inviting Da-Chuan. Yeah.
Yes, thank
so this, I mean, the classification is like 0 plus 1D. So there's nothing that talks about chiral, like,
Yeah, it's more like a bulk classification. It's classifying the bulk phase space chain insulator, which by dimension reduction, it turns out in all dimensions, the phase space chain insulator boils down to a 0 plus 1D classification.
yeah, so I think I can understand that part, but somehow this edge state of that is like the Fermi surface, which should like if you think in terms of chain insulator, it's more intrinsic, right? Like even if I don't have any symmetry, it should be robust. Like that, at least not in every dimension, but like in 2 plus 1 or 10 plus 1, and so it's not a symmetry protected. It doesn't require symmetry to protect it, but somehow that's different, right? So when you have Fermi surface, maybe you're never in that case. Maybe you always have like superconducting instability. So
yeah, I think if it is gravitational anomaly, then it's like a perturbative anomaly, and then you cannot trivialize by interaction. There's no SMG. I think. Yeah, you are right. So I think you mean that there is a stability for this chiral mode. This as they are chiral, they should be stable. So here we investigate something that is not protected by. There's no gravitational anomaly. It's protected by some Z4 symmetry. It's not even U1. So we are able to create a small enough symmetry group to allow non-perturbative anomaly, to allow symmetry interaction reduced classification. Yeah. It's like the wild fermion. You may think wild fermion is also very chiral, but actually it has a Z16 classification if the symmetry is only Z4.
that's a 3 plus 1 case.
Yeah, that's a 3 plus 1 boundary of a 4 plus 1 quantum Hall effect.
Yeah, but 1 plus 1 will not, the
1 plus 1, you will not be successful in doing that.
Yeah.
Actually, that's a good question.
Okay, thanks. See you.
you.
Bye. Bye.
Like to, so
Oh, I'm a host. I can end.